Hello, ladies and gentlemen. Good morning, good afternoon, good evening, wherever you are. As usual, it's another week, and we are continuing with these quality management system talks on process control, which is our podcast number 6. Last week, we did 6.1 and 6.2 on samples management and introduction to quality control. This week, we are going to do two talks back to back on quality control for quantitative tests and quality control for qualitative tests. So I'm going to start this one off with quality control for quantitative tests. And before I do that, as usual, if you want to get in touch with me, my contacts is joundo, Joundo 664 at gmail.com. I will post this also in the comment section. So please hit my YouTube channel and let's interact. So the learning objective for this podcast is that at the end of this podcast, you will be able to do the following. One, differentiate accuracy and precision, select control material for the laboratory, establish acceptable control limits for a method when only one level of control material is available, explain the use of a Levy-Jennings chart, and describe how to correct out of control problems. So let's start by looking at what quantitative tests do. Quantitative tests measure the quantity of a particular substance in a sample. Let's say the quantity of sugar in a fizzy drink. And also quality control for quantitative tests are designed to assure that patient results are accurate and reliable. Not just accurate, but accurate and reliable. The implementation steps for qualitative tests control is to first establish policies and procedures, assign responsibility, and train the staff. As I always say that, if it is left to everybody, nobody will do it. So you have to assign who is the responsible officer and also train all of your staff on these procedures. Select high quality controls, establish the control ranges, develop graphs to plot control values, also known as Levy-Jennings charts, monitor the control values, develop procedures for corrective action, and record all actions taken. Our mantra in the lab is that if it has not been written down, it has not been done. So in order to know what is happening, then you want to record everything that you're doing, which will show you whether there's a problem or there's no problem. And if there is a problem, the actions that you have taken, both the corrective action and the preventative actions. Let's define what a control is. A control is a material that contains the substance being analyzed and include with the patient samples when performing a test. So let's say that you want to analyze blood sugar. So the control has to have that sugar in it. And this must be included with the patient samples when they're performing a test. The control is also used to validate the reliability of the test system and is run after calibrating the instrument and also run periodically during the testing process. There's a difference between calibrators and controls. So briefly, let's look at the difference and similarities between these two. A calibrator is a substance with a specific concentration, while a control is a substance similar to patient samples that has an established concentration. Calibrators are used to set or calibrate the measuring points on a scale, while controls are used to ensure the procedure is working properly. So one is used to set the points on a scale, the other one is to ensure that the procedure is working properly. The characteristics of control materials are comprised of appropriateness for the diagnostic sample, values cover medical decision points, and they are similar to the test sample or matrix. They are available in large quantity, ideally enough for 1 year, and can be stored in small aliquots. so that you don't go to the main vial every day or every time that you want to run a control. And these control materials may be frozen, may be freeze-dried, or chemically preserved. And they also require very accurate reconstitution if this step is necessary. So you want to follow both the MSDS, the manufacturer's instructions, and also the standard operating procedure that you have established in your lab during the reconstitution phase. This is true both for controls and also external quality assurance panels that we will cover in another podcast. These control materials can be commercially prepared. They can also be made in-house by the lab themselves. They can also be obtained from another laboratory. Usually, a central or a reference laboratory will be providing these. Now, when the control material has been assayed, then it means that the target value has been predetermined, and you just verify and use it. But when it is unassayed, then the target value has not been predetermined. It means that you have to perform a full assay before using it. If, on the other hand, it is an in-house control material, for example, in-house pooled sera, then a full assay and validation are required before use. When we choose the control materials, we have to look at the values that cover medical decision points. And these materials must be similar to the test sample, and the controls are usually available in high, normal, and low range. So when you look at the patient medical decision points, there will be critical high and critical low, abnormal high and abnormal low, and the normal range. So the controls have to cover all of those ranges. So you would have one control that covers both critically high and low ranges, another one covering abnormal high and abnormal low range, and the other one covering the normal range. You want to make sure that your controls are prepared and stored appropriately, and we must adhere to the manufacturer's instructions. If they have to be stored at -80 or in CO2, liquid CO2 or room temperature, we must adhere to the manufacturer's instructions and to keep adequate amounts of the same lot number. We've witnessed instances where the controls are not working, and by accurately recording the lot numbers, we've been able to get back with the vendor, and vendor has been able to verify that there was a problem with that lot number, and they were able to replace the whole batch of the lot number without cost to our laboratory. So, as I said, they must be stored correctly the way the manufacturer has instructed. Now, let's briefly look at the steps of implementing a quantitative quality control. One is we obtain the controls material, whether this is commercially prepared, in-house, or from a central referral laboratory. And then we run each control 20 times over 30 days. After we've done that, then we calculate the mean and plus and minus 1, 2, and 3 standard deviations. After we've done the standard deviations, then we measure the variability. The variability is a normal occurrence when a control is tested repeatedly. And this variability can be affected by 3 things. It can be affected by the operator technique, it can be affected by performance characteristics of the measurement, or environmental conditions. So the goal here is to differentiate between variability due to chance from that due to error. And in order to do that, we take those measurements, like we said, over a 30-day period, and we also plot the frequency. Then we would look at that data and see whether it is distributed around a central value, and if we get a normal distribution or a normal curve. And then we have to look at the measurement of central tendency. We can look at this through 3 ways. One is through the mode. And this is the value which occurs with the greatest frequency, and it will be right at the middle. Not necessarily right at the middle, but we look at how many times it has occurred, and it will be the one which is occurring at the greatest frequency. Then the median is the value at the center of the midpoint of the observations. So if, let's say, you've got 14 observations, then the seventh value would be the median point, and then the mean will be the calculated average of the values. So as I said, for example, you have 14 values, 14 measurements, and the frequency is there. Then you look at the mode, the one which is right, the median which will be the one right at the center. Then the mode is the one which is occurring most frequently, and the mean is the calculated value. So we use symbols to perform these calculations. We use the symbol sigma, which is the sum of the added data points, and small n, the number of data points, x1 to xn, which would be all of the measurements from 1 through n, whether n is 100 or 20 or 30 or whatever the number might be. X bar would represent the mean. So in order to calculate the mean, which is x bar, so the mean would be equal to x1 plus x2 plus x3 plus x4 plus x5 plus xn, xn being the number of measurements. And then we divide that with n, small n, which is the total number of measurements, to give us the mean. For example, in ELISA test, where we want to calculate the mean, we run the control 20 times in 30 days, and we record both the optical density and cutoff, that is the OD and CO values for each measurement. We divide the optical density, that is the OD, by the CO, OD divided by CO for each data point of all observation, and this standardizes the data. Once we've done that, we add the ratios and divide by the number of measurements to get the mean. So we'll have a series of answers, let's say 192, 194, 196, and so on, until maybe 204, 208, 212. Then you may get a measurement of, let's say, 270 or 280, which would obviously be an outlier because it's very different from the other observations. Now, I will not go into a lot of detail on what we do with this outlier, but we want to go back to the experiment, to the measurement, whether it was an experimental error, or it was a correct observation, or you simply have to remove it. When you plot those means, then they will give you a set of tendencies. They will give you a normal distribution, which is a bell-shaped curve, and all the values are symmetrically distributed around the mean. And this is assumed for all quality control statistics. So quality control is used to monitor the accuracy and the precision of the assay. And I'm going to go delve into slightly more on this. What are accuracy and precision? Accuracy is defined as the closeness of measurements to the true value. Accuracy is the closeness of measurements to the true value. Precision, on the other hand, is the amount of variation in the measurements, while bias is the difference between the expectation of a test result and an accepted reference value. So if we take, for example, a dartboard, and we throw the dart and we hit the bull's eye all the time, then it means that we are both accurate and precise because we are hitting bull's eye all the time. But we may be hitting to the left or to the right consistently around one point away from the bull's eye. It means that we are precise, but we are biased either to the left or to the right or to the value of that point where we are hitting on the dartboard. But if we are throwing our darts and it is hitting all over the place, then it means that we are imprecise. So for standard deviation and probability, when we take a set of data with a normal distribution a random measurement will fall plus or minus one standard deviation 68.3% of the time. And that measurement, that random measurement, will fall within 2 standard deviations 95.5% of the time. And it will fall within 3 standard deviations 99.7% of the time. Now you want to determine whether you want to use 1 standard deviation or 2 standard deviations, and look at where your data is falling all the time, your measurements are falling all the time. So the standard deviation is the principal measure of variability used in the laboratory, and we all know what the standard deviation statistical formula is. You can refer and define what it is. We will not go into that here. However, we use the standard deviation divided by the mean times 100% to determine the coefficient of variation, which is the standard deviation expressed as a percentage of the mean. So coefficient of variation is used to measure precision, to monitor precision, and to compare methods, and should ideally be less than 5%. The CV, or coefficient of variation, as I said, is used to monitor precision, is used to compare methods, and ideally should be less than 5%. So let's delve into how to develop the Levy-Jennings chart on a graph and how we are going to use it. So as I said, we go to assay the control material at least 20 to get 20 data points over a 20 to 30 day period, and ensure procedural variation is represented. Then we calculate the mean and plus or minus 1, 2, and 3 standard deviations. So we measure 20 data points over 20 to 30 day period. We ensure procedural variation is represented, and we calculate the mean and 1, 2, and 3 standard deviations. Once we've done that, then we plot that on the graph. We plot the mean and we draw the line of the mean. Then on the upper side, we plot the straight line of plus 1 SD, plus 2 SD, and plus 3 SD. And then on the negative side, that is on the lower bottom of the graph, we plot the minus 1 standard deviation, minus 2 standard deviation, and minus 3 standard deviation. We indicate the chart name and the lot number of the control, which would have been calculated from 20 controls. Then daily we plot the control measurements, and then we look for bias, for trends. Now, the interpretation will depend on the number of controls which have been run with patient samples, and it would be good if one control and accept results if the control is within plus or minus 2 standard deviations, unless there is a shift or a trend. It would be better if we use 2 levels of controls, and in this case we apply the Westgard multi-rule system. How would we detect the error? 2 types of errors: random error and systematic error. So when there is variation in QC results with no pattern, and only a cause for rejection if it is outside 2 standard deviations. So when the error is random and it is outside the 2 standard deviations, then it is a cause for rejection. But if it is within the 2 standard deviations, then we do not reject it. On the other hand, for systematic error, this is not acceptable, and we must correct the error, the source of the error. For example, if there is a shift and the controls are on one side of the mean for 6 consecutive days, or there is a trend, the controls are moving in one direction, heading towards an out of control value, whether to the positive side or to the negative side. So when you look at the plots on the Levy-Jennings charts, and you see that your observation points are all to one side, plus 1 standard deviation, plus 2 standard deviation, plus 3 standard deviation, and they are not on the negative side, then it means that there is a shift to the positive side or to the negative side, as the case might be with the observation that you have made. But when you observe that your points are tending towards plus 1 SD, plus 2 SD, plus 3 SD, and tending towards getting out of control, then that indicates a trend, and they must be rejected. Now, when we measure uncertainty, this represents a range of values in which the true value is reasonably expected to lie, and it is estimated at 95% coverage. The more precise the method, the smaller the range of values that will fall within 95%. For most instances, a range of plus or minus 2 SDs is accepted as measurement of uncertainty that is explained by random variation. If the QC is out of control, you must stop testing and then identify and correct the problem. Repeat testing on patient samples and controls after correction. Otherwise, do not continue testing. Also, if the QC is out of control, as I've indicated, then do not report patient results until problem has been solved and controls indicate proper performance. So how do we solve out of control problems? First is we must identify the problem through root cause analysis or whatever system that you use. And then we refer to established policies and procedures for remedial action. Some of the possible problems could be degradation of reagents or kits, the control material degradation, operator error, failure to follow manufacturer's instructions, an outdated procedure manual, equipment failure, or calibration error. Any of these 7 sources could be the reasons of the problems that you're seeing with the controls. So in summary, a quality control program for quantitative tests is essential. It should monitor all quantitative tests. It should have written policies and procedures followed by laboratory staff. We must have a quality manager for monitoring and reviewing QC data. We must use statistical analysis and provide for good records. And lastly, provide for troubleshooting and corrective action. The key message to take from this podcast is that a QC program, a quality control program, allows the lab to differentiate between normal variation and error. And the QC program monitors the accuracy and precision of lab assays. The results of patient testing should never be released if the QC results for the test run do not meet the laboratory target values. I'm going to repeat this again. The QC program allows the lab to differentiate between normal variation and error. The QC program monitors the accuracy and precision of laboratory assays. And lastly, the results of patient testing should never be released if the QC results for the test run do not meet the laboratory target values. Thank you so much, and I welcome, as usual, your questions, your comments, your concerns. My email address, as I said in the beginning, is joundo664@gmail.com. Thank you, and see you in the next one.